All right, I think we're ready to go. Thank you, Srinivas. And again, as Srinivas says, my name is Doug Malcolm, and I'm with a group here within MSC that does engineering consulting services. A lot of people aren't familiar that we have that capability, but it's a great job, and I get to do a lot of really different, interesting types of simulation. And as part of that, I have a chance to do a lot of stuff in explicit dynamics, and that's what we're going to talk about in the next 30 minutes or so. And I'd like to take a few of those minutes and kind of go through and explain to you how explicit works within Nastran, how we've implemented in some of the strengths of our code. So, as I say, quick agenda here. In the next 30 minutes or so, I'd like to give you a brief primer on explicit analysis within the MSC Nastran suite of tools. I always like to start that with why simulation. It's always a good question to ask whenever we're doing simulation. And we'll talk about that a little bit. I'll show you some examples of explicit types of simulation when we answer that question, and I think you'll see. Hopefully we can make a good case. So the fact that a lot of you are here already to see about explicit simulation leads me to believe that you're probably accepting of the finite element technology, computer simulation in general, but this is the next level. And it's a specific application, but it's a very interesting application. And we'll talk about when it's appropriate to use explicit simulation. Then we'll get in and just, after we talk about explicit simulation in generalities, we'll talk about how, again, it's implemented in the MSC Nastran tool and some of its unique capabilities and strengths. Following that, we'll look at pre- and post-processing. How do we set up the models? How do we prepare a model to run an explicit analysis? And then how do we look at the results once we've run that explicit simulation? Again, I think we'll show you that our tools are very capable in that regard. I have a number of slides that I'd like to show you that kind of gives you an idea of what typical applications are. That's always a good way to learn the capabilities of code. If you can see something that looks similar to your particular needs, then it's, hopefully a flag goes up and says, this might be a good fit for explicit simulation. And we'll talk about that. I'll show you several of those and some of the decisions that we need to make when we decide to do these types of simulation. Towards the end, I'd like to take a few minutes, probably 5 or 10 minutes, and we'll actually go into our preprocessor Patran, and we'll set up an explicit dynamic simulation, and I'll show you the basic steps. And I think if you're finite element users in general, you'll see that it's very familiar, and there's very little different that you need to do. And we'll set that up. We'll run it, and in fact, we won't actually run it. I've already run the simulation, but then we'll pull up the post-process. I'll show you how to run it, and then we'll pull up the post-processor, and we'll look at the results and give you an idea of what you typically might do in the post-processing phase of explicit simulation. And then we'll get into a brief summary, and then we'll do a Q&A towards the end. So let's get started here. Product development challenges. Every manufacturer that's out there has their products, and all these products have questions, and they want to know, want to answer these questions before they spend the money to design and build and sell these products. And some of the questions that they might ask are, is it durable? Will it fail? Is it safe? Will it perform? Will it meet the expectations and the requirements of their particular product? Is it crashworthy? Obviously, the aerospace and the aircraft and automotive industries are very interested in crash safety, and you'll see that explicit dynamics is probably one of the biggest players in that industry. And then also post-mortem, why did it fail? We can look at and do simulations to determine so that we can resolve that and hopefully prevent that from happening again in the future. So these are all great. These are all great questions to ask. We can always do physical testing. That's really the proof in the pudding, is that when we do a physical testing and we see that our components, our design, our system survives a physical test, then we can feel good about it. The problem with that is that physical testing can be very complicated. It can be very expensive. I was at a customer recently, and we talked about doing simulations in a turbine engine where a bird gets ingested and you might have a blade in that turbine engine that gets lost, causes the engine to go out of balance. And a physical test for a full-scale physical test on a jet engine can be somewhere in the order of a few $1 million. So you can see very quickly you get very, very expensive. And in a lot of cases, it's destructive. You don't have a component. So what happens if your part fails and you don't have a success during that test? You don't have a successful test. Now what? Well, hopefully what we can do with simulation is we can give you a tool to do these tests virtually. Do a virtual test, and we can evaluate whether or not our components, our assemblies are going to survive, and if they do, great. And then we can still do testing. We don't hope to replace testing. What we hope to do, our goal is to reduce testing. So if we can reduce testing, if it's a $3 million test, that's a $3 million savings. Obviously, there's some things like in the upper left there where it's a cell phone and we drop that. That's not going to be a $3 million test, but you're going to get limited data out of that because it's going to happen. It can still be fairly expensive, but with a virtual simulation, a virtual test, we can get any number of output results that you might not be able to get from physical tests. So our ultimate goal to keep in mind is how can we reduce physical testing? So because of the topic here, we want to talk about explicit. When do we do explicit simulations? Hopefully most of you are familiar with finite element technology. Typical finite element analyst is used to seeing implicit codes. Nastran is one of those implicit codes. Well, now we have an explicit technology that's embedded within Nastran that we're going to talk about a little bit more. But let's just talk about, well, when is explicit technology appropriate? I have a checklist, and what you see on the screen is this checklist. The first thing I ask myself, is this a dynamic environment that's not suitable for a static or a steady state type of simulation? Those types of simulations, static, steady state, you can probably do implicit. But if you've got a dynamic environment, you should at least ask yourself, is explicit simulation appropriate? And then at that point, okay, maybe I decide I have a dynamic event. Now, how do I know whether I should use explicit or implicit technology? And I'm going to talk about what the differences are in those in just a second here. But the next question I should be asking myself, well, how long is this event? If it's a very short duration event, that also leads me to believe that explicit technology is inappropriate. You'll see that because of the technology, and we won't get into all the details of it, because of the explicit solver technology, there tends to be very short time steps. And that means to do any duration, dynamic event of any significant duration takes a lot of these time steps. Well, as you get longer and longer, you can see that it may not be all that practical because each one of those takes a lot of calculations. Implicit dynamic simulation in that situation may be more appropriate. But there's a lot of situations where exactly what we're talking about here, short duration events, dynamic events, that makes it very appropriate for explicit dynamic types of simulation. Kind of a secondary capability or function of explicit types of dynamics is look at the extent of nonlinearities. It turns out that this technology is very robust in terms of nonlinearities. We can handle, and we'll talk about the types of nonlinearities that we can deal with, but it is very robust, and there's not a significant cost increase that goes along with that, as opposed to implicit technology where there is. Finally, the last bullet here, large problem size. We'll see that the computational costs will go up linearly with the problem size. So if we have twice the model size, we have twice the runtime. It's simple as that. Implicit, that's not the case. As you go twice the model size, because we have these large matrices, they go up by the square of that size. So typically, and again, it comes down to the level of nonlinearity. Implicit codes typically will have to fight convergence issues. If you're having an implicit nonlinear code, you may have to turn the knobs, as we say, to tweak to get that converged solution, especially as the nonlinearity level goes up. So if we take those bullets and we put those in a graphical form, we can see essentially what's on this slide. So on the upper left there, first let's talk about the extent of nonlinearity. So you'll see that there's virtually no penalty in an explicit code. That's the flat line that you see across that. there's virtually no penalty for nonlinearities in explicit codes. That's a huge benefit. You have a highly nonlinear system, and it doesn't cost you any more to have that highly nonlinearity. We can increase our fidelity, get more accurate solutions, and we can get a better overall result. Conversely, in that same graph, you can see that implicit goes up exponentially as we get to higher and higher levels of nonlinearities. We're always searching for that magic convergence point with implicit codes. In some cases, they're appropriate. In other cases, it makes sense to look at explicit technology. If we move over to the upper right on this slide, you'll see that as the problem size goes up, so does the explicit cost in a linear fashion. Again, as we double the model size, we double the runtime, or the CPU cost. And that's very, you can expect that. It's very predictable. Implicit, not so much. You'll again have these large matrices that you have to deal with. They're square, they'll go up with the square of the problem size increase. Finally, on the bottom, you'll see that in this situation, implicit actually has the advantage. If we have what we call long physical problem time, so our event duration is long, as we go longer and longer, again, it's linear. So explicit goes up linear, implicit will come down, and as it reaches steady state, you'll see that the additional cost for the implicit solver is lower. So there's a situation where maybe it makes more sense to do implicit code. So just a brief comparison between those. Again, a little bit more on that in the explicit. Its very nature dictates that we're going to have small time steps. And the one thing that's interesting about that is it's dictated by the model and not by the analyst. So in an implicit, you can go to bigger time steps, but it's up to the analyst to decide what's an appropriate time step, whereas in an explicit, it's going to be a function of the model. So explicit also has the advantages that there are no big matrices and no matrix inversions are required, so we don't have to deal with extremely large stretch files, if you will. I think we've all fought that. This space is cheaper now, but it's still becoming an issue as people get more and more complicated simulations. And again, I'll say on the explicit side, very, very robust solutions when we have high degrees of nonlinearities. Now comparing the implicit, again, the advantage, if we do have a longer event duration, we can go to larger time steps, but we do have some disadvantages. We have big matrices and matrix inversions, and I think we all know that there's other technologies that we don't require these matrix inversions, iterative solver techniques. So that's not necessarily as bad as it may look, but it's certainly something to be considered with. And then finally, the last bullet there on implicit, the procedure complicated with increasing degrees of nonlinear, then absolutely, for the people out there who've done nonlinear implicit code, you guys are all familiar with the challenges of always getting a converged solution. Talk about nonlinear briefly. Just like with the implicit codes, we divide and categorize the nonlinearities into three categories. Large deformation. Now, large deformation includes not only large displacements, large rotations, it also includes large strain formulations. So most of our element technology has these large strain formulations because of the very nature of these types of simulations tend to be large strain. So we handle that. That's all part of the code, and there's no extra cost that goes along with that. Contact allows us to have interactions between various parts of the structure, whether you have different components or a single part that's going to fold back on itself. We can deal with that very, very simply using the contact creation. And then the final nonlinearity we'll talk about are material nonlinearities. Well beyond the linear elastic realm, we can deal certainly with all the standard engineering materials like aluminum, steels, titaniums, where we have an elastic plastic response. The other thing that I like to bring up when we talk about materials is the fact that because these tend to be short duration events, we've already said that, and we've also said that they can be large strain. We have a large strain in a short duration, and that's going to give us high strain rates. We have technologies, we have techniques to deal with these high strain rates. And often, especially in very short scenarios, short duration scenarios, it's appropriate. And of course, we need to know what those material properties are, but at least we have the capabilities that we can deal with it. And the final bullet here under materials is failure. We can deal with the failure of specific materials. So we have ways that can allow elements to fail and basically be removed from the problem. That's also very, for these types of problems, that's a very good capability. This is a bullet that I like to throw in here because kind of going the other way, there are situations where we do implicit in our consulting services, nonlinear implicit types of problems where we'll have extreme difficulty reaching a converged solution. Well, we've already said that these explicit codes tend to be very robust in terms of nonlinearity. So in some situations, you may take what could be a static or steady state type of simulation and turn it into a dynamic simulation that then we run with explicit technology. And because of the robustness of the nonlinearities, we can get to a solution that we might not otherwise be able to get. So that's kind of an outlier, but it is, we've had situations where we've used that and it's very powerful. A couple of slides here talking about within our explicit technology, we actually have two types of solvers. We have a Lagrangian solver and we have an Eulerian solver. And I just wanted to throw a couple of slides to give you an idea of what the difference between those are. For those that are familiar with implicit types of finite element, that's typically considered in explicit world, that's a Lagrangian solver. So it's a finite element formulation. It's based on finite element technology. And it's a discretization of the structure, just like you would with standard implicit codes, like Nastran's and other codes out there. Let's see. So for structural dynamics, which is what we're going to be talking about here, we've already said these are dynamic type problems. We'll typically use a Lagrangian mesh to simulate the structural part of the problem. And these types of Lagrangian elements technology will result ultimately in elements of constant mass. So you can see the graphic here. It shows a deforming structure. Each of these elements will maintain that mass. And you'll see in the next slide while we're talking about this conservation of mass. But the explicit technology with the Lagrangian solver is very similar to the implicit in that it has nodes and elements, and the elements are surrounded by those nodes or corner nodes, and those nodes have forces that are dictated by the strength or stiffness of the elements. Very similar again. Now, conversely, an alternate technology is the Eulerian solver, which is also part of the Nastran or explicit solvers typically. At the bottom there is an example of this. This is a stationary mesh. If I were to show you that mesh, it happens to be a very fine mesh, so I don't show it, but you'll find that the elements don't move. What's moving in that is the material from element to element. Essentially a fluids problem. So we apply initial conditions in this. It's a bullet hitting a flat plate. We apply initial conditions here. We define what the materials are, where, and in this case the bullet would have a velocity, and it gets projected towards this plate. Now the thing that you want to take away from this is that we can handle structures with Eulerian technology by giving the material model strength, just like we do with Lagrangian. We can define a yield strength, we can define hardening capabilities. We have several material models for Eulerian capabilities as well. The differentiator between when we use Eulerian and Lagrangian solvers is Eulerian solvers tend to work very well for systems that have extreme deformation. And you can see in this case, the bullet looks nothing like it did at the beginning as it did at the end. And that's a typical application for Eulerian. But I'm going to show you some other capabilities of this where we can tie these together, the Lagrangian and Eulerian. So now let's talk about MSC Nastran and how do we implement this technology that we're talking about. Well, what we do is we take what we consider the best-in-class solver technology and we embed both of those underneath the MSC Nastran umbrella. We take the LS-Dyna, which if anybody's familiar with explicit technology, certainly the most widely used explicit code out there. We embed that within Nastran, and in addition to that, we embed our MSC Dytran product, which is an Eulerian solver product. And we embed both of those within the MSC Nastran tool. If you're a Nastran user, the access to that would be what's called a Solution 700. That's just a keyword that would flag that this is an explicit solver, and you don't need to know that. We're going to show you in our demonstration that we'll never have to even mention it. But for those that are out there that are Nastran users. So again, these are typical. Application would be short duration transient events, drop test, impact, crash simulations. So we'll talk about some other ones that are kind of unique, these blast, sloshing, bird strike, where we actually tie both of these solvers together within a single Nastran run, explicit run. So these are fully nonlinear solutions. Like we said, there's really no cost. And in fact, you typically would not turn, and there is no technology to turn off the nonlinear capabilities. Inherently, it is nonlinear. The other thing that's really powerful about this is that we're going to use a Nastran-style input and environment. And that's fantastic for the guys that are already Nastran users. They're already familiar with the input requirements. Very little difference in setting up a solution, explicit solution otherwise. So for the new users, they don't have to learn Dytran and Dyna and multiple codes and tie them together and have what we'll sometimes call tie-in codes. You don't have to learn that if you just learn Nastran, MSC Nastran, explicit. So from a high level, we've got within MSC Nastran, we've got Lagrangian, typically used for structures, Eulerian, typically used for fluids, and those fluids can have strength, and that will allow us to simulate structures with a fluid representation. We have some very powerful technologies that we call coupling that allows you to couple the Lagrangian and Eulerian solvers together and have an interaction between that fluid and that structure. That's a subject for a later webinar in the next month. Srinivas will talk about that a little bit. But it's a very powerful technology. Again, full nonlinear support. We have contact, large deflection, comprehensive material models, and then some other bullets here that are very interesting. Parallel processing. If you have multiple processors on your machines, we can take advantage of that. We have some ocular simulation using the LSTC. LSTC is Livermore Software Technologies. That they're the authors of the LS-Dyna program, so they're very proven. Have some very powerful techniques as well. We include that in our Nastran explicit. So some of the powers here allows, this explicit analysis allows Nastran users to use existing models, so we can bring in existing models, and you'll see me do this in the upcoming demonstration. So you've already got models there at some point. Common modeling environment, we can use familiar preprocessors, post-processors. If you're familiar with Tatran or SimExpert, those are our pre- and post-processors. And we use one. We don't have to have multiple different environments, multiple different codes to pre- and post-process our simulations, these explicit simulations. We have what we'll call multidisciplinary support for these explicit. And an example of that would be this fan blade out simulation we talked about, where we might run the turbine blade up to a certain pre-stressing rotational velocity to get some stress in the turbine blades, and then we might throw a bird at it that might come in and damage a blade. That would be an explicit simulation, whereas the pre-stress would be an implicit. And then after the bird comes in, there would be some out of balance. We could do a rotordynamics, which would also be implicit. So we'll call that chaining, simulation chaining. And I've already briefly touched on interaction between Lagrangian and Eulerian solvers, and I think that'll become more clear when we show you a couple of slides later on. A couple of other capabilities that are important, HPC, high performance computing, distributed memory parallel. So not only can we take advantage of multiple processors on the same machine, we can take advantage of processors on a cluster, so we can distribute the solution requirements of our simulations. Comprehensive material and element library, we'll show you a little bit more about that in just a minute. We do support the LS-Dyna native output plots, such as D3 plot, bin out, D3 THDT, standard outputs of LS-Dyna, and you'll see. Now that's essentially what comes out of a Nastran explicit room. We do have this chaining. I'll show you an example of that, where we can take Nastran implicit, tie it to an explicit, and then go back to an implicit, so a chain of simulation. And we do have full support by our pre- and post-processors, SimX and Patch. Last couple of bullets on the capabilities here, and then we'll get into some examples. We do have a progressive failure, or PFA, technology that allows a simulation to calculate failure of elements and a progressive failure of elements. At a certain time, some element may fail, And then at the next time, its neighbor may fail, and you can watch cracks grow and things of that nature. And the final bullet here supports time domain noise, vibration, and harshness. This is a relatively new technology, a new request by our customers, and that's available to you at this level. A little bit about contacts. We have capability to go between deformable bodies to other deformable bodies, or deformable bodies to rigid bodies, or a single deformable body, and it can self-contact. And a lot of times these crash simulations, because there's so many parts, it's difficult to have individual contact bodies. So what we can do is just take and make in the lower right-hand corner here, we can make the whole truck a single contact body and say, okay, I want you to check yourself for self-contact. And it's very simple to set up. And we'll show you in our demonstration. We're going to do it shortly here. We also have the capability within contact that if you do have elements that fail, they're taken out of play. They're no longer considered for contact. So that's a neat technology, and again, gives us a higher fidelity resolution for our solution. Materials, we've touched on these briefly, but here's just kind of a list of all kinds of metals, plastic, elastomers, ribbon, so several different types of constitutive relationships that could be used to these. But certainly the most popular are the elastic plastic, and in many cases that includes not only yielding, hardening, but strain rate effects as well. Pre- and post-processors, again, we hope that you're using our products. We believe our products are very good. Certainly they're going to have the highest level of support for the explicit technology capabilities within MSC Nastran. And those Dytran, SimExpert are the two most well-known. Other preprocessors that support Nastran can also feed this. You may have to make some modifications, but we can certainly set up in other codes as well. Post-processors, there's quite a few available to you. Again, our standard tools, Dytran and SimExpert, are available to you and do post-process. So those are available, but then there's some other shareware. Aero uses shareware, free code, that does a nice job for presentation. CEI Insight is an extremely powerful tool and does fantastic presentations. We use it quite often. And LS Pre-Post, which is a post-processor used by and created by LSTC, makers of LS-Dyna. So here's kind of a matrix, if you will, and all kinds of different types of simulations. I won't get into each one of these. I put this up here. It just gives you something to think about. Some examples, upper three here from the automotive industry. Obviously, regulations are required for all of these. So there's a lot of physical testing that goes on. And again, our goal here is to reduce that physical testing, not eliminate it. But if we can reduce some of that physical testing, there's a real benefit to that. Some examples down in the lower left is a defense type application, penetration through armor. That's obviously becoming a very high interest type of simulation. In the middle is a blast simulation on a building. Again, that's something that might not have been done 15 years ago, but now there's an interest in it. And then there's a lot of work that's done in consumer products, drop testing, packaging, whether it be a cell phone by itself or TV in a foam housing. So let's look at some different examples here, and this is the upper left. These are typical of what you'll see as the output of these explicit simulations. Pipe whip is a situation where we do a fair bit of refinery work in our consulting services. If you have piping in close proximity to other piping and you have a catastrophic failure, what you don't want is to have this catastrophic failure in the pipe cause it to whip around and tail other pipes. So we can do evaluations, and that's what you're seeing in the upper left. Crash simulations, obviously, probably the single biggest user of explicit type simulations is in the automotive industry. A lot of crash simulation going on. Transportation industry as well. Again, a lot of regulations. In this case, it's a barrier for a train, and you can see the nonlinearities that we talked about. There's a lot of contact there. Definitely large deformations, post-buckled scenarios after the sheet surface of this train buckles, all kinds of contact and adaptive type contact. Again, another crash simulation. This is a neat example in the fact that we know that a single crash simulation is very complicated. Well, if we put three vehicles together, it gets even more. This one's got nearly 1 million nodes, so nearly 1 million 6 million degrees of freedom. And these can be extremely long running. And you can see that very, very complicated types of scenarios. If you were to look at the run times on that, if you run it with a single processor, it can be on the order of 24 hours, pretty long. But because of our capabilities of taking advantage of multiple cores, we can bring that down. This benchmark, we bring it down to from about 24 hours down to about 50. Pretty significant reduction in solution time. Simulation that you might not have seen 15 years ago, right? These are things that are now being considered that make sense to do with explicit. This is a fan blade out that I was talking about. We'll start off with an implicit solution stress. Then we'll throw a bird at the blade and see how it damages. In the video on the right, it's actually an explosive charge that releases the blade to simulate that fan blade out or bird strike. And you can see how violent those dynamics are. So we can do an implicit pre-stress, an explicit code of the blade, and then we can follow up with the rotordynamics or the airframe. Guys want to know what kind of loads are going to come into my airframe if something like this happens to one of your engines. Again, we can all do that whole sequence all within MSC Nastran. A couple more slides, and then we're going to do a quick demo. The bird strike simulation here, this is the Lagrangian, represents the turbine blade, and then we throw this fluid representing the bird at the blade, and we look, and if you look carefully at those turbine blades, you'll see that there's some failures there. Sloshing is becoming more popular. Why would you want to do sloshing in the case of a ship tank? That may be a stability issue. You don't want the fluid within your ship to get to the point where it can roll your ship over. For car fuel or for car tanks, fuel tanks, a lot of interest recently in the noise that comes out. Very undesirable as cars get quieter, and the perception is that I don't want to hear that distinctive booping noise when you have that car fuel tank moving around, stopping quickly, accelerating quickly. That's an undesirable feature. And so we can tie a explicit solution together with some of our capabilities for acoustics, our new FFT solver. Again, very interesting types of technologies. The last one I want to show you here again is the interaction between, in this case, it's a blast into a structure, a semi-cylindrical steel structure. And a blast wave comes, hits that, and it actually fails that steel structure, and then the blast wave travels through the hole where the structure is stable. Good example of fluid structure interaction with failed surfaces. And again, that's a subject for a future webinar, so you'll see that within the next month. So what I'd like to do now is do a real quick demonstration. And I'm going to bring up our tool, Patran. This is our preprocessor, Patran, and I'm going to create a brand new problem. And very quickly, I'm going to create, and I'm into the preprocessor, and I'm going to, very simply, I'm going to say I want this to be an explicit nonlinear solution. So now we're set up, and it's context sensitive, so Patran knows now that I'm working and thinking in terms of explicit. I'm going to import the previously existing Nastran deck. All right, and this is going to be a bottle, and this is a bottle that I want to drop on the ground. So I'm going to import the model, it's a previous model, and it gives me lots of statistics, and if I import that, now you can see what this model looks like. In Patran, I can change the background colors if I want, and I can also change how this is displayed. So if I want to make this shaded, I can. All right, I'm going to leave it wireframe for now. What I'm going to do, because this came in from a different type of Nastran simulation, I'm going to go in and I'm going to create a material property that's appropriate for our explicit. I can name it anything I want. I know what the properties are. And I want this to be an elastic plastic material. I'm going to make it aluminum, so I'm going to give it density that's appropriate to aluminum. I'm going to give it a modulus of 10 million, Poisson's ratio, and I'm going to give it a yield stress and a hardening modulus that tells the code what the material should do after it reaches its yield limit. As long as I'm here, I'm going to create another material for our floor that we're going to drop it on. As I say, we're going to do a drop on this model, so I'm just going to create another rigid material, and I'll just leave the same materials in there for now, and that really doesn't matter because it's going to be rigid. Okay? So now, next step here is I want to update our properties. We've got some shell that came in from our previous model. So I'm going to just go in and assign the newly created material that we just created to the properties that came in along with that. Now the thickness is appropriate. Still I want it to be 30,000 thick, so I'm going to say, okay, that's fine. Okay? And as long as I'm here, I'm also going to create a new property for my rigid floor. And for that, I'm going to use that material that I just created. I'm also going to give it an arbitrary thickness of 10,000. Okay, now what I want to do is I want to create a floor. My model of the bottle is all updated to explicit, very simple, right in the geometry. Now, Dytran has a way to organize the model in what we call groups. I'm going to create a new group for the floor so that I can easily organize this model. Very quickly, I'm going to create a surface that is going to be representative of that floor. I have many different options. I'm going to create just by dimension, and I'm going to make it a 6 by 6 floor. And I know the location of this bottle because I've seen this model before. I'm going to center that underneath the bottle. So there's my floor. I can very quickly go in and create a mesh on that. So I'm going to select that floor. I'm going to give it a mesh density and select the existing property of that one that we just created that was the rigid. So now when I push the button here, now I've got a rigid floor. Okay? So and I can look at this in any different manner. I'm going to look at straight on. Because now my model is set up. Now it's time to set up the dynamics of this event. Well, we want this to be a drop scenario. So first thing I want to do here is I want to have interaction between these. So I'm going to go to my loads and boundaries conditions, and I'm going to create a contact body. And I'm going to create my first contact body. It's going to be the bottle with 2D elements. And I can just select, based upon the finite element model, select those elements. So now I have a contact body that is representative of the bottle. Let's do the same thing for the floor. Select the floor, the elements that go along with the floor. So now I have contact definitions. As simple as that. By default, all the contacts are going to be hit all the other contacts. So it's very simple. Now what I can do is I can fix the floor. We don't want the floor to move, do we? So let's click. We'll put a displacement constraint on that. Call it fix, and I'm going to fix it in all 3 degrees of freedom. And I'm going to tell it that I want to fix the nodes on the floor. All right, so now I've got the floor fixed. Now I've got a couple of things to do. Let's first put some gravity in here. Let's put an inertial load, solid gravity, and I want that to be minus 386.4 consistent units in a global Cartesian system, and I can just say gravity is now defined. Now, I want to make this a little more interesting. Let's rotate that bottle over a little bit. And the way we can do this is we can use our organization. I can say, let's transform, rotate, and we're going to rotate the bottle about the y-axis, and I'm just arbitrarily going to choose 12 degrees. And let's make sure I check the original group that both the bottle was in. And now I've got the bottle oriented over. So hopefully this is going to be a little more interesting. So at this point, I've got everything set up. I've got my contacts. I've got the floor held. I've got gravity turned on. The last thing I need to do for my loads and boundary conditions is to define the drop height. Well, you may have asked yourself, well, you built it right on the floor. Well, we don't want to pay for the computational cost for dropping this thing, and I'm going to choose a 48-inch drop height. So what we can do is, using energy methods, we can calculate what the impact velocity of the bottle is going to be when it hits the floor. A very simple calculation, and for this case, for a 48-inch drop, that would mean minus 192 inches per second. And I'm going to assign that to all the nodes in the bottle. And refresh this. So very simply, I can take all of those. Now we have an initial velocity, and so we're basically simulating a 48-inch drop. The last option, the last item that we need to do is we need to basically define how long we want this to be. Again, the defaults most of the time are adequate for this type of simulation. So I can just go and tell the code that I want to do it for 20 milliseconds. And at this point, I'm ready to go. I've set up the whole simulation from importing the model, setting up the contacts, told it how long I want it to be. And now I can push the button, and I could say solve. I've already done that, so we don't have to wait. It does take a couple of minutes for this to solve. So let me just go ahead and let's assume that 3 minutes like a cooking show. And we're going to go in and let's take a look at these results. These results come in an D3 plot, which is the format that's written by LS-Dyna. Select on that code. Okay. And I'm going to read that information. Okay, and now what I can do if I want to is I can go create a plot. Let's plot deformation. I typically like to look at deformation before anything. Let's create an animation. And I'm going to do a couple of switches here. I just want it to be shaded. I don't want to see the undeformed. And I want to do this in 3D so I can rotate the animating view around 50 frames and pushing the button. And now you can see we've dropped the ball, it's deformed. We can see how it deforms. Maybe I say, okay, that's great, that looks interesting. Let's also maybe look at some stresses. And we can animate that as well, and I like to turn on the edges when I do this. So now you've seen displacements and stresses, and we could even go look at plastic strains if we want. We have the options to look at any kind of requested output. So that's a full explicit analysis in a very short period of time, something less than 10. So if we go back to our presentation here, and let's just summarize. So in summary, hopefully the primer has given you the idea that we want to use explicit when we have short duration transient events, and also that you go away with knowing that MSC Nastran, the explicit capabilities, or explicit with Nastran models. You saw me reading that existing model. We have a common modeling environment, so we can use the same preprocessor for all these different types of simulation. That gives us the ability to chain these things together very simply. Simple setup, it's fully nonlinear. We have Euler capability for the fluids and fluid structure interaction, which we're going to see in a future webinar. And that's it.